Hello, so in today's video we're going to be looking at where Newton's third law comes from and deriving it from considering the conservation of momentum. This is important because Newton's third law is often the one people find most confusing, so I think it'd be good to show where it comes from. And it's also important because as Newton's third law is a result of the conservation of momentum, what we can say is happening with regards to Newton's third law is just momentum is being conserved. And momentum being conserved means that we can describe classical mechanics in terms of momentum and positions without worrying about forces, and this is very important if we're generalising classical ideas to the quantum world. So this will be an overview of how we get Newton's third law from momentum. So to start with, we're going to have a brief overview of Newton's laws. If you're watching this video, I'm assuming you're familiar with them, but I would like to go over them briefly so we have a clear grounding on what laws we'll be using during this video. And we'll go particularly into depth concerning Newton's third law. So firstly, Newton's first law can be summarised by saying that if a particle doesn't experience any net force, then it won't accelerate. That is, its velocity will not change. And what this means is if there's no forces acting on a particle, it will either remain stationary if it's stationary, or if it's moving, then it will keep moving at the same speed and in the same direction. Newton's second law says if there is specific force acting on a particle, then it will experience acceleration if there is a net resultant force. And it quantifies the relationship between this force and the acceleration. And the way it does this is it thinks, well, if an object has a large mass, then it won't accelerate very much. So as mass gets bigger, then for a fixed force, the acceleration must decrease. And so we can formalise that, and we end up with the equation F equals ma, which is the net force on something is equal to its mass times its acceleration. And lastly, we get Newton's third law, which is that equal and opposite forces exist. So if I push against a wall with a particular force, the wall will push back on me with the exact same force. So the forces are equal, it's just they're acting in opposite directions. If I'm pushing forwards on the wall is pushing backwards on me. So they act in opposite directions. And now we're going to look at deriving the third law from conservation of momentum. But as a quick reminder, Newton's third law, if we think of forces, says that the action force F1 is equal to minus the reaction force, which is F2. And I put a minus in there because F1 and F2 are acting in opposite directions. So if one force is positive, the other is negative, but they have the same size. That is, the magnitude of F1 is equal to the magnitude of F2. And so now that's derived Newton's third law, which was that F1 is equal to minus F2. So for this, imagine the person is initially standing stationary on the boat, and the boat is stationary. So the initial total momentum of the person and the boat is 0. So we have P total, i.e. the total momentum is 0. But momentum is conserved, so when the man or woman moves off the boat, like steps off the boat, then the boat must also move but in the opposite direction so that the total momentum remains zero as the person is kind of pushing off of the boat. So we get that the momentum of the person plus the momentum of the boat must equal zero, which implies that the momentum of the person is minus the momentum of the boat. And if the boat and the person were both initially stationary, then the change in momentum is just equal to the final momentum, because the initial momentum is zero. So we get the momentum of the person when they push off the boat is equal to the change in momentum, where the change in momentum is the momentum they had before pushing off the boat compared to the momentum they have when they push off the boat. And we can say a similar thing for the momentum of the boat. So we get the change in momentum of the person is equal to minus the change in momentum of the boat. And if we divide both sides by any amount of time passed, then we get the change in momentum of the person divided by that amount of time is equal to minus the change in momentum of the boat divided by that amount of time. And if you remember that force is defined to be change in momentum over change in time, which is an alternate way of writing F equals ma, what you end up with is that the force on the person is minus the force on the boat, so F1 is minus F2, and this is Newton's third law. So we have proven Newton's third law by considering the conservation of momentum. And as I said, this is very important because this allows us to write Newton's third law as a specific example of the conservation of momentum, which allows us to do classical mechanics without even making direct reference to forces. And it also allows us to generalise classical physics to the quantum case. I hope you've enjoyed this video. If you liked it, please check out my other videos. I hope to see you for more videos soon. And thanks for watching.